We're going to talk about electricity and voltmeters today. The reason we're going to study electricity and learn a little bit about electricity is we want to test the power supplies in our computers, and we want to be safe doing it. So let's do a quick little rundown of electricity, how it works, what it is. Electricity, we all should know, we plug something into the wall and it works, it lights up. We have two major kinds of electricity. We have alternating current and direct current. Let's talk about alternating current for a second here. First, let's understand electricity and the movement of it. So electricity comes from electrons, moving electrons, and electrons are the orbits of an atom. So we have an atom with a nucleus here, and we've got protons and neutrons in them, even numbers of protons and neutrons. Then we've got a ring around them, 2 rings, 3 rings, depending on the atomic element, and these have electrons in them. Electrons are negatively charged things, whoops, it's an E, that are attracted to the nucleus, kind of like our planets in our solar system. They're sucked into the sun. The gravity holds them there. These electrons stay in place. Now, sometimes we don't have a complete shell, our valence shell, and if we've got an uneven number or a smaller number than you could fill, because each ring can hold a certain amount of electrons, they float, they can escape easily, and they become free electrons, and they can move to another atom if there's a spot. So if I have another atom over here, that's the outer shell, here's the neutron, and I've got gaps here. Here's an electron, and here's an electron. This electron could hop into one of these gaps here easily. This right here is an example of a conductor. Conductors conduct electricity. Good conductors are atomic numbers, I believe it's on the right side of the periodic table, that are heavy metals. So for example, most metals, I think all metals, I take that back, are conductors of electricity. Mercury, it's a liquid metal. They used to use them in our old thermostats. When the temperature would rise, a spring would load, the lever would tilt, and the mercury would roll over, make contact, and conduct the electricity. Some are better than others. Gold is better than copper. Copper is better than tin. So depending on where it is on the chart. But metals are essentially a conductor. On the opposite side, if we've got a atom and the electron valence is full, electrons aren't going to be able to escape or add in easily. It can happen, but it doesn't happen easily, and we call these insulators. Good examples of insulators would be rubber, plastic, air. Air's a conductor, or excuse me, insulator. Not to say that electricity cannot pass through this. Lightning is an example of that, but just kind of an idea. So let's see. Let's start a new page. Save. Okay. So electricity is the flow of electrons. Okay. We have insulators and we have conductors. The conductor allows the electricity to flow on it, and that might be a wire. Okay. Electricity has to go somewhere. So usually what happens is we'll have a battery, like on a car, a plus and a minus terminal, or like the little 9-volt batteries. They have to look, the plus and the minus, if you look closely, you'll always see that. The wire has to make a complete circuit. Okay. So electricity flows from positive to negative. So here's the electrons flowing, and they'll do that if you take a wire and connect it to both ends of the battery. If you do that, though, you've created a short circuit, and you're going to fry the battery or the wire. Okay. Think of electricity as a garden hose or water flowing through a pipe. That flow is the potential power it has, the voltage, and if you turn off the water, open that up here, nothing's going to flow. Okay, once we turn on the water or make that connection again, the electricity is going to flow. Okay. Oh, how did I get my thing so small? Shoot. Size. Okay, the electricity is going to flow again. If we purposely want to stop the flow of electricity, we can put a break in there, something we'll do, and it's represented by this, a switch, okay? If we were to open the switch, notice we have a gap here that electricity can't flow. As soon as we close the switch, we bring this down and we make that contact, the electricity can flow. Again, I said we're going to have a short circuit if we do that. So we need something in here. So typically what we'll do, we'll have a circuit. A circuit needs to do something or something in it. And maybe in this circuit, we're going to have a light bulb. Okay, that's my great drawing there. Okay, a light bulb, just like everything electric-wise, needs inside and an outside. We call that positive or negative or neutral and hot, depending on the application. We'll talk about that in a minute. So the electricity will come through here, flow up through this filament. The electricity flowing through here will excite it, get it hot, and it'll actually glow and turn on. It might be a motor, it might be a television, but the idea is the same. So if we want to stop this, we can open the circuit, put a switch in there, disconnect it from the battery cable, and the electricity stops flowing, okay? This is a battery, and batteries are DC, direct current. We also have AC, or alternating current. Okay, alternating current is what we see in our house. DC is typically a car. Think about a car, the battery of a car. That's a 12-volt DC system. If you don't think about for a minute, what is the alternating current in our house? It's approximately 110, 115 volts. AC plus or minus, 10 points or something like that. So it can go up to like 120 volts down to 109, 115 in that range, but it's about 110 volts, okay? If we were to look at an oscilloscope, it's a tool that measures voltage. We would see on an oscilloscope, on an alternating current, the cycle, the signal would look like this, up and down. It would just keep repeating that, up and down. And each cycle, up and down right here, right here, I get it, is one cycle, 1 hertz, cycles per second. Our electricity on an AC cycle is 60 cycles per second. So if you were to, have you ever got shocked with electricity and you feel that voltage, that's that cycles per second, that's that up and down thing. This is AC. On a DC system on an oscilloscope, we don't have the same signal. We have a square wave. It comes up, over, down. Now, on an alternating current on this oscilloscope, this right here is 0 volts. This mark right here is about 110 volts. Down here, let me make a new page here so I can draw a level. New, don't save. Okay. On an alternating current, much better, okay? We have 0 voltage, we have 110 volts, and we've got negative 110 volts, okay? So alternating current can go negative once it reaches this point at 0, and this is 1 cycle, and this right here is 60 cycles per second, a second, okay? On a DC, this is AC, on a DC system, same tool to do this, an oscilloscope, same scale, same measure, this is 0. We typically have, in smaller electronics, 5 volts. This is plus 5 volts. Now, we don't have any negative voltage in DC, so it's either on, like that, at 5 volts, or off, at running at 0. On, off. You might have recognized this or seen this before. This is how, this is binary. It's either on or off. Remember or look at your computer. Have you ever noticed this symbol? You have this circle and this line through it. That's kind of the universal symbol for power, meaning 1 for on or 0 for off. So yeah, just kind of a little nerd nugget there. On a DC system, well, on our computers, what we're doing is we're taking a plug that's coming from the wall, and the wall plugs into a receptacle. Looks a little bit something like this. Another one down here. It's got a, like that. Same thing down here, like that. And it's got a faceplate on it with a little screw right there. If you've looked carefully too, you'll notice that one of these is longer than the other one. Typically, not always. Newer ones are. That's showing us which one's the hot one. The little one, that's the dangerous one. That's the one that's going to bite us. The big one is the return line. We need both to make it work. Remember that circuit. So we have our power source here, comes in, comes out. In the case of our battery, we had a plus and a minus terminal. On alternating current, we have it coming out through this one, doing whatever it does. In this case, maybe hitting a light bulb again, coming back and going into the return. Notice we have 3 spots. We've got the hot, the common, and this is the ground. It actually goes to your fuse panel and goes straight to earth, plugs a stick in the ground. That's the representation of ground right there. So we have 3 wires, 2 wires in DC. Let's see what else. Oh, I was going to mention, so we've got our computer, okay? We plug it into the wall, into this little dongle thingy up here, okay? This is alternating current. So what's happening is the current comes up to here, up to something, and of course it has to go back. So if we only had 1 wire, it wouldn't work. So we've got 2 wires, possibly 3 in a cord. If we have 3 wires in a cord, that third one is the ground, and that's typically green, okay? Whatever this is converting our power from alternating current to direct current, which is what's used inside of our PC. All of our components are DC. Now we have different voltages. Can you name or think of the 3 different voltages that we have inside of our computer? A good guess would have been 5 volts right off the bat. So we have a 5 volts DC, we have a 12 volts DC, and we have a 3.3 if you did the reading, okay? The 5 volts runs the controllers and things that spin, that draw a lot of power, run the 12 volts. The 3.3 is power for the Pentium processor. If you've got one, we'll learn about the connectors and the different power things on our computer. But what's happening here when we're working with our computer, we're converting this alternating current in our wall to a device that's kicking it down or swapping it from AC to DC. And we call that a converter, or a transformer. We can also convert. We can also go from DC to AC. Have you ever seen someone have a blender that they plug into their car for a tailgating party? That's converting the car's DC voltage to AC. It's going the opposite direction. We call that an inverter. This one we're converting AC to DC, 3 different voltages. And the thing that does that on our computer is called the power supply. And that's kind of what we're talking about here today. So know that if you're working on a computer and it's plugged into the wall, you've got 110 volts coming into it. So you got to be careful, okay? Once you're beyond the power supply, those cords that are coming off, a typical power supply will have a plug on the back, and it'll come off. It's detachable. And then on the other side, we'll have, depending on how big your power supply is and how many watts, the connectors. And these connectors will either be 3 volts, 5 volts, or 12 volts. Now, the connectors have a bunch of wires on them, and each wire might do something different. Only one of these would have power on it. The others do something, a return line or a signal or something like that. Right, so let's talk about our power supplies for a second. So if you have not seen one or paid attention to one, they're just a square box, okay? Now these are what we call solid state units. If they go bad, we throw them away. There's vents on it. You'll probably notice that behind, or you can see it, there's a fan that spins. On our original computers, this fan and the power supply was enough to cool our entire computer. Not so much nowadays. We need additional cooling. We'll talk about that in chapter 12, I believe. But you'll see a fan on it. You'll see the place where the power cord plugs in, and it's keyed, so it can only go in one direction. You might see some power supply or power connectors that have 2 wires like that. Most of them will have 3, and remember that third's the ground wire. You also might see a switch, a slide switch, like this, that lets you switch where you are worldwide. How can I say that better? Some countries don't use our voltage system, 110 volts. In the UK, they use 220. So you might have a switch or a slider for a switch that allows you to switch between US and somewhere else in the world by flipping that switch. You might also see some power supplies will have their own power switch, which is kind of nice. So you can still keep it plugged in, but flip the power off on the power supply. And then we've got this goes to the receptacle in the house, plugs in there, and then on the other side we'll have wires going to the computers. Okay. Now, to make electricity work, remember we have to have a loop. Okay, it has to be a complete circuit, come and go. If it's broken, it's not going to work. So when we're working with 12 volts DC, 5 volts or 3 volts, we have a, how can I describe this easily? A ground, okay? The negative part. Now on the motherboard, let's think of our car for a second, okay? You got your car and a battery inside that car. There's the hood, okay? In here's a battery with a plus and a minus. Your plus goes, it's a big red cable, right? If you ever had to jump a car, it goes down to the starter on your car, the starter and the alternator, everything that's all connected together. The ground goes straight to the frame of the car. Your entire car is grounded. This is why in a lightning storm, they say stay in your car, because not only are you insulated, but everything's grounded. So you've got a better chance of not getting struck by electricity, but that's mostly because of the tires. They insulate, you're not touching the ground. On a motherboard and the case and the computer, everything is connected to the ground, okay? There's a wire that physically goes and physically touches this, and then when you plug your cord from your, this is a motherboard here, a MOBO, plug your cord into the main motherboard, and it's a long power connector. One of those is the ground, the negative, and that goes to the actual motherboard itself. If you look at the bottom of motherboard, or look at the standouts where the motherboard gets screwed into the motherboard, or to the tower, the case, there's metal there, and that's ground. So when the screw goes through that and connects to the case that is, you know, screwed into, the case is grounded, the motherboard's grounded because of this screw touching that, and all the components. So if I've got a capacitor or a resistor, well, not a resistor, but a capacitor or an inductor or something like that, part of this is going to be connected to the motherboard, the ground, and the other one goes to some hot wire somewhere, okay? We're getting a little bit beyond, but just understand that we need 2 wires to make everything work, the hot and the ground, and everything's grounded. So if you happen to be out on site working on someone's computer and they don't have a grounding strap or an anti-static mat or something like that, you can set the computer on the table, touch the case, anything bare metal, and you've just become to the same potential as that computer, and you shouldn't fry anything with static electricity, okay? Just kind of a, you know, keep that in mind. Let's see, safety. When we're working on our computers, we open up the case. There's 4 screws on our power supplies. Again, if it's burnt, throw it away and go get a new one. You can get a brand new 400-watt power supply for around 50 bucks now. They're super cheap. There are components in here, and they probably could be fixed, but if you calculate it, our labor, you know, we're charging 100 bucks an hour for someone to, you know, fix their computers. The time we would take to take this apart, solder it, desolder it, you know, all that stuff, it's cheaper just to go buy a new one. Plus, it's safer. IET Electronics, maybe they'll go do that kind of stuff and you know, fix a blown circuit or something in here, but we'll just swap it out. So safety, only remove the 4 screws that hold this to the back of the case, okay? You'll see like this and the opening here, and then those 4 screws will release it from the frame of the computer, and then the power supply can come out and you can actually hold it, replace it, unplug everything. What we're going to do in lab is we're going to plug in the computer while it's live, so you need to be very careful to remove your jewelry. Don't have anything dangling into the computer. Be very careful because you can get shocked. You might think, well, I've got tennis shoes on, I can't get shocked. Well, hypothetically, that's true. Have you ever worn tennis shoes and stuck something in the receptacle? You can still get bit because electricity is going to find the shortest path to ground. So if you happen to have sweaty feet in your shoes, it's going to jump from your feet to something metal. So you still can get shocked. If you're in the space shuttle floating in space and you're floating, you're not even on ground, yeah, you got a better chance of not getting electrocuted. But just be careful. We're going to work with a live power. So we're going to take the case off, the side off of our case, and we're going to plug in the computer. We'll turn it on, and we're going to take our probes from our voltmeter, and I'm going to show you this on I'm going to make a second video attached to this where I'm actually going to demonstrate the voltmeter and how to use it. Then we'll use our voltmeter and we'll get some readings off some of these cables here, okay? Then what we'll do is we will pull the power supply out of the computer, plug it in again, and we'll take more readings and see what we get, okay? Then when we're done, we'll plug it back in, connect it again, turn it back on. Hopefully we've connected everything. If you're starting off fresh here and you've never taken apart a computer, maybe take a picture of where all the cables go. If you're familiar with it, you've been in a few times, it's not going to be that tricky. You'll know exactly where everything go. When we're putting our computer back, we should have no extra wires dangling. So count how many free ones you have, and then count how many used ones you have. Maybe, again, take a picture or something like that. You'll know each device, everything in our computer, if you've got a CD-ROM or a DVD, you know, whatever you happen to have, it needs power. It's going to have a power cord if it's not built into the motherboard, okay? Some things that we plug into the peripheral slots will draw power from the motherboard connector, the PCI or whatever, AGP, whatever slot that happens to be, okay? Let's see, anything else I want to talk about here? I think that's it. We'll talk about the rest on the second half of this video, so I'm going to stop this, and then we'll go and take a look at a real live voltmeter in action, okay?